Welcome, everyone. Today, we'll explore k-free numbers and the generalized Möbius function, diving into fascinating connections with square-free theory. Last time we showed that square-free integers have density 6 over pi squared, which can also be written as 1 over zeta of 2.
Right. So a bit more than 60% of integers are square-free, and that magic constant came from zeta of 2.
Recall that square-free means that in the prime factorization of n, no prime shows up with exponent 2 or larger. We proved that the proportion of integers up to x that are square-free approaches 6 over pi squared, or equivalently 1 over zeta of 2.
So square-free is like the k equals 2 case. Are we going to look at numbers with no cube factors, no fourth powers, and so on?
Exactly. We will see that the same strategy works for all k, and that zeta of k always controls the density. Our guiding question is, how common are integers that avoid any prime to the kth power, not just squares? Let us start by imagining we forbid cubes instead of squares and see what changes.
My guess is that avoiding cubes should be easier, so cube-free numbers should be more common than square-free ones.
We generalize by saying an integer is k-free if no prime to the kth power divides it. So the familiar square-free numbers are the case k equals 2, and cube-free numbers with no cube factors are the case k equals 3. Up to 30, we only need to remove multiples of 8 and 27, since those are the cubes in that range.
So 8 and 27 drop out, but numbers like 4 or 9 are still allowed for cube-free, even though they are not square-free.
This small list hints that as we raise k, more integers qualify, and our job is to measure that precisely. To really understand k-free numbers, it helps to look at prime factorizations.
So we want to translate the condition of avoiding prime powers into a statement about the exponents in the factorization.
Write n as a product of primes to various exponents. These exponents will encode the k-free condition. An integer is k-free exactly when every exponent in its prime factorization is strictly less than k.
So square-free means each prime appears at most once, and cube-free means each prime can appear with exponent up to 2.
This shows the property is multiplicative, because the condition factors into independent rules on each prime. This exponent viewpoint will make our counting argument and our generalized Möbius function feel very natural. Now, we set up a counting function for k-free numbers, just like we did for square-free ones.
So we are looking for the analog of q of x that counted square-free integers, but with k-free instead.
We write q sub k of x for how many integers up to x are k-free. We again use inclusion-exclusion, with the Möbius function keeping track of which prime power conditions we are including or excluding. For each n, we construct an indicator that equals 1 when n is k-free and 0 otherwise, by summing Möbius values over divisors whose kth powers divide n. Summing that indicator from 1 up to x gives this formula, where for each divisor d, we count how many multiples of d to the k lie up to x.
So this really looks like the square-free formula, but with every square replaced by a kth power.
From here, the rest of the story is to approximate this sum and read off the main term for large x. Now we turn the exact formula into an asymptotic, isolating the main term as x grows.
Is this the same move as before, where we replace the floor by x over something and control the error?
We write each floor as x divided by d to the k plus an error that is less than 1 in absolute value. When you add up those small errors over all relevant d, their total size is controlled by a constant times x to the 1 over k. The main term is x times the sum of Möbius of d over d to the k, and that sum is 1 over zeta of k, giving our density. This equation summarizes the story. Q sub k of x is x times 1 over zeta of k, plus a smaller error term of size about x to the 1 over k.
So, just like for square-free numbers, the zeta function is encoding the exact density, now at the point k instead of 2.
We can already see the general pattern. For each k, the density of k-free integers is 1 over zeta of k. Let us plug in some values of k to see what the densities actually look like as numbers.
I want to compare the k equals 2 square-free case with the k equals 3 cube-free case to see how big the jump is.
For k equals 2, we recover our familiar value. About 60.8% of integers are square-free. For k equals 3, the density is around 0.832, so more than 80% of integers are cube-free.
That is a big jump from 60 to over 80% just by moving from squares to cubes.
At k equals 4, the density is about 0.924, so more than 90% of integers are fourth power free. As k grows, these densities keep creeping closer to 1, meaning almost every large integer is k-free for big K.
So the square-free case is actually the most restrictive one, and every higher k gives a looser condition.
Let us work out a concrete example of our formula when k equals 3 and x equals 100.
That will give a sanity check that the density prediction matches actual counts.
We want the exact number of integers up to 100 that are cube-free. The divisors d that matter are those whose cube is at most 100, namely d equals 1, 2, 3, and 4. We plug in Möbius values for these d. 1 maps to 1, 2 and 3 map to -1, and 4 maps to 0 because it is not square-free.
So we expect 85 out of the first 100 integers to be cube-free, which lines up with the density of about 83%.
Here we count multiples of 1, 8, 27, and 64 up to 100, weight them by the Möbius values, and arrive at 85 cube-free integers. If you list out the multiples of 8, 27, and 64 and remove overlaps, you will find there are exactly 15 non-cube-free numbers up to 100. So far, we have used the usual Möbius function. Now we build a version tailored to k-free numbers.
So mu k should play the same role for k-free numbers that mu played for square-free numbers.
We look for a function mu k such that a simple divisor sum built from it tells us whether n is k-free. Just like the classical Möbius function, this generalized version is multiplicative, so we only need to define it on prime powers. It turns out that on a prime power, the generalized Möbius function is non-zero only at exponent 0 and exponent k-1.
In the k equals 2 case, this recipe should collapse back to the classical Möbius values on primes and their squares.
On each prime power, mu k takes value 1 at exponent 0, -1 at exponent k-1, and 0 everywhere else. With this definition, the sum of mu k over divisors whose kth powers divide n is 1 exactly when n is k-free and 0 otherwise. So, mu k is the natural generalization of Möbius that inverts the operation of attaching kth powers. Finally, let us connect the density formula to Euler products and a probability viewpoint.
This is where 1 over zeta of k factors over primes, right?
Euler showed that 1 over zeta of k can be written as a product over all primes of 1 minus 1 over p to the k. The product breaks into one factor for each prime p, and that factor is 1 minus 1 over p to the k. You can think of 1 minus 1 over p to the k as the probability that a random integer is not divisible by p to the k. If we imagine the divisibility conditions by different primes behaving independently, then the product gives the probability of avoiding every p to the k at once.
Because 1 over p to the k shrinks fast with k, each factor gets closer to 1, and their product moves closer to 1 as well.
This probabilistic reading of the Euler product explains in a very clean way why k-free integers become more and more common. Let us step back and summarize what we have learned about k-free numbers.
I want to see clearly how all the pieces, like q sub k, mu k, and zeta of k, fit together.
First, k-free simply means that in the prime factorization of n, every exponent is strictly less than k. Second, We built an exact counting formula for q sub k of x using Möbius-weighted inclusion-exclusion over divisors whose kth powers divide n. Third, as x grows, q sub k of x behaves like x divided by zeta of k, with an error smaller than a constant times x to the 1 over k.
So mu k gives an indicator sum for k-free numbers, and the Euler product for zeta of k explains why the density splits into prime by prime factors.
The key message is that the square-free density 6 over pi squared is just the first instance of a family of densities controlled by zeta of k. Before we wrap up, try a quick check to see if the pattern for densities and zeta of k feels solid. For the practice question, use the rule we have been repeating for each k to write down the density when k equals 5.
Following the pattern, the density of 5 free integers should just be 1 over zeta of 5.
Exactly. The same Möbius argument tells us that q sub 5 of x is approximately x divided by zeta of 5. For reflection, think in terms of the Euler product. Why should the product over primes of 1 minus 1 over p to the k move closer to 1 as k grows?
Because each factor removes a probability of 1 over p to the k, and those probabilities shrink rapidly with k, the total amount removed from 1 gets smaller and smaller.
If you are comfortable with that reasoning, you have a strong grasp of how k-free numbers, Möbius functions, and the zeta function fit together. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.